Hello everyone, this is Felix from GMWolf. Today we're going to look at how to make a smooth movement top-down system. So, to begin with, we have this simple layout with a player sprite, which looks like this. It's quite important to have it facing downwards, as you can see if I add the sprite here. I have the arrow pointing downwards. This is because of the way we're going to calculate our direction later on. Next, we have two different wall sprites. We have a square wall sprite and a corner wall sprite, like so. I already made two objects, so obj wall being our normal square wall sprite, and obj wall corner being the triangular wall. And in a room, I already set up a small level, like so, so that we can use it later. If you're wondering how I managed to get those corner sprites rotational, if I place it somewhere in the world, like on the right over here, now zoom in on it so you can see it clearly on the video, and I click flip X or flip Y on the left in the object tab, as you can see I can easily flip the X and Y direction. This is really useful when making, for example, platformer games, because more often than not I can see people's project with like loads of different sprites for every single direction of the block, when really you can simply do it inside the room editor by pressing the flip X and flip Y button. So what we're going to do first of all is create a new object, which is going to be our player object. So I'm going to name it obj_player. Now what we want this object to do is not only move smoothly, depending on what buttons we press, but we also want it to collide with the objects. So we're going to quickly create another object right now, which we're going to call obj_par_wall. This will be our parent wall object. We're going to be using this as a parent to all of the wall objects, so that we can have a single collision check inside our player object to collide with our walls. So if you haven't seen parenting yet, or how it works, I have made a video about it, and I will put a link to it in the description and maybe an annotation in the video as well. So now that you created your obj_par wall, we're going to go back inside our wall and both our wall objects over here, and under the parent bit we're going to choose obj_par wall. So we're doing this now just as preparation for our game. So now go back to the object player player object, and choose the sprites to be SPR player. Alright, the first thing we want to do is set up a few variables. So let's add an event, create event, and put in a code block. This is going to be our key bindings. So let's write key bindings. And for those of you who don't know, the / at the top of your code window defines kind of the name of that code block. So if I press OK now, as you can see, the code block is called key bindings. And if I change that to key bindings 101, for example, and press OK, it will say key bindings 101. So as you can see, this is really useful. If you're going to have multiple actions, you can see which one does what. So let's define our key bindings. We want to be able to have two sets of keys. We want to have the arrow keys on your keyboard as well as W, A, S, and D. So what we're going to define is our normal key bindings and our alternative key bindings. So let's first define our normal key bindings. So we're going to do key_up is equal to VK_up. Then key_down is equal to VK_down. Key_left is equal to VK_left, and key_right is equal to VK_right. Now you may be wondering, why would you do it that way when you could just put VK up, VK down, etc. all the way throughout your code? The reason is, if the player wants to change those keys, you can just add a very simple system that will change those variables. So it's really easy to change, and you won't have to go through all your code in order to change your key bindings. Now we're going to set up our alternative keys. So we're going to be key underscore up underscore alt is equal to ord, which will give you the key code for a certain character, and then we add in speech marks, W, speech marks, close. Now, I capitalized W. I'm not sure if this is entirely necessary. I've just always seen it that way, so it is best practice to keep it that way. Next, we do key down alternative is equal to ord S, key underscore left, alt is equal to ord A, and key underscore right alt is equal to ord D. Now, you could add more key bindings here for different things. If you're making a game where you need to interact with different objects, you may add, a certain key for it. Maybe you want to have an inventory, and you need to have an inventory key. There's a bunch of different key bindings you might want to add into this code. So we're going to press OK, save the changes, and now we're going to add another piece of code. This piece of code we're going to dedicate to the variables for movement. So we're going to call it movement variables. And if I press OK now, you can see it is very, very useful to name your blocks like this, because now I can easily see which block I'm supposed to click on to get to edit the code I want. And I find it a lot nicer to divide it in different code blocks. It doesn't tend to affect your performance at all, and it does mean you have it is much easier to find what code you're dealing with, especially once you have a lot of code in a single object. So for movement variables, we want first of all the basic one. So we want movement speed, which will be your maximum speed. We're going to set that to 5. And next we want facing angle, which is going to be the angle you're facing at. This is the same as image angle, but we're going to create our own variable just for more control. Next, we want to define axes. So the way we're going to get else move movement to work is by defining some axes. What those are basically, you can imagine them as a point on a line, and when you press right, it will move towards the right end of that line. When you release it, it will tend back towards the center. If you press left, it will go towards the left point of that line, and then come back to the center. So it's kind of like, I can't think of a real world analogy for it, but it's kind of a sliding effect that you can use to, not to have a sudden movement. You ease into it. So what we're going to have is, first of all, define our axes. So I'm going to make a small annotation here to make sure we know it's the axes. We're going to have axis underscore x to be equal to 0, because we want to start off at the center, and axis underscore y to be equal to 0 as well. Now I want to define the maximum value. So axis underscore x underscore max will be equal to movement speed. Movement speed. We're going to do the same thing for axis y, so I'm just going to copy and paste this down here and put y. And our max and minimum value are going to be the same, because we don't want it to be faster to go right than left. That wouldn't make much sense. So we're just going to keep it as axis x max and axis y max for now. Now we want to define more variables, which are the acceleration value and the restitution value. So acceleration value will be how fast it is to go to one end or the other of that axis line. And the restitution value will be how fast it goes back to the center. So, when you release the keys. So when you press a key, it will use the acceleration value to go either right or left. When you don't press any keys, it will use the restitution value to ease back towards the center of that axis. So we're going to have axis underscore x underscore acceleration is equal to 0.8. This could be set to anything. If you want your player to accelerate faster, you could place a higher value. If you want him to accelerate slower, you put a lower value. And axis underscore y underscore acceleration is equal to 0.8. Now, axis x and axis y acceleration are both going to be the same in our project right now. However, it may be the reason why we're using two different variables for everything is you may need in some projects to change it. For example, if you're on a if you're making a side-scrolling game, you may want it to be faster to go left and right than up and down, or the other way around, fast to go up and down than left and right. So we're leaving all those variables in so that we can change it later much more easily without having to change our whole code. Now we're going to add axis underscore restitution, x underscore restitution. Let's set this to 0.6. Now those values I have tried before and I found they worked really, really nice. So I'm not just making them up. I did try them out, and I think for a simple project, if you're making a top-down shooter or something like that, they tend to be pretty good if you have, you know, sprites that are 32 by 32. So this is it for our movement variables. So we can press OK, and we're just going to quickly save the project. And now we can start adding the actual movement code. So let's add an event, step, and add in some code. This will be movement, so we're going to call this movement. So first of all, what we want to do is get our key presses. Now, our key presses we'll only need during this single piece of code. So we're going to be defining them as temporary variables, you know, local variables. So we're going to put var heat pressed ed underscore up is equal to keyboard underscore check key underscore up. Now we also want to check if key up alt is pressed. So what we could do and it is what we're going to do, is simply go pressed up is equal to keyboard check vk up or keyboard check key underscore up underscore alt. I think that's what we called it. Yeah, perfect. So now, if the up key is pressed or the alternative up key is pressed, pressed up will be equal to true. Otherwise, it will be equal to false. Now we can do the same thing for all the other ones. So I'm just going to copy and paste this 3 more times. Remove this and go pressed down is equal to key down, that is, or key down out. Next, key left is equal to keyboard check key left or keyboard check key left out. And finally, pressed right is equal to keyboard check key right or keyboard check key right out. Here you go. So now we have whether or not our keys are pressed. Now what we want to do is start calculating our axes. So what we need to do is define the direction in which our axes will be moving. So we're going to call this compute axes, and now we have var axis underscore x underscore dir is equal to pressed underscore right minus pressed underscore left. So what we're doing here is quite interesting. What we have to remember is that in GameMaker, true values and false values are actually stored as numbers, where true is 1 and false is 0. What this means is that we can actually add and subtract them from each other in order to do some really quick maths without having to deal with Boolean values. So in this example, if we have the right key pressed, press right will be equal to 1, and we take away whether press left is pressed or not. So if you only have the right key pressed, then it will be equal to 1, so direction is positive. If, however, we only have the left key pressed, then we have 0, because the right key pressed is not being pressed, minus 1, because the left key is being pressed. And so you get minus 1. So the x direction is therefore equal to minus 1. What we can do now is do the exact same thing for the y direction. So I'm just going to copy and paste this again, right here, and do axis y there is equal to key pressed down minus key pressed up. Because remember, in GameMaker, down is positive, up is negative. So what we want to do now is calculate the acceleration and restitution values. So first I'm going to do acceleration. So acceleration. Var axis underscore x add. So this will be how much we have to add to our axis every step, is equal to our direction, axis underscore x underscore dir, times our acceleration values. So axis underscore x underscore acceleration. So remember, axis x acceleration we already defined inside our create event to be 0.8. So now if we press right, we'll be adding 0.8 every time. If we go left, we'll be subtracting 0.8. I'm just going to copy this again and change it with axis y. So axis y add is equal to axis y dir times axis y acceleration. Now let's do the restitution values. Now restitution is slightly more complicated because we need to check when the keys are not pressed, and we don't want it to go further than our 0 value. So we have to go restitution, and we're going to do var axis underscore x sub, which is how much we're going to subtract, and this is equal to, so first of all we want to get our restitution values. So axis underscore x underscore restitution, and we want it to be, let's see, right now if we have axis x restitution, it will be subtracting our restitution value every time. However, if we're close to the 0 point, we don't want it to be we don't want to subtract too much. What I mean is, right now our restitution value is of 0.6. But if our current axis is actually at 0.1 and we subtract 0.6, we'll be back to minus 0.5. But we want it to stop at 0. So what we have to do is make sure that our restitution will never be greater than our current axis. So we're going to use the function called min, which will return the smallest value of all the arguments we put in. So we have axis min, axis x restitution, and then the absolute value of axis underscore x. So what the absolute value is always the positive value of it. You can think of it as the square root of the square of whatever you put in. So for example, the absolute value of 1 is 1, and the absolute value of minus 1 is still 1. Now, what we want to do is make sure it is always in the direction, in the correct direction. So remember, this is how much we're subtracting. So say our axis is on the positive end of the axis. We want to subtract a positive number for it to get lower. And if we're on the negative end of the spectrum, we want to subtract a negative number, i.e. add a positive number. So we're going to multiply it by the sine of our current axis. So to clarify, right now what we have is this will return either will return the smallest value between our restitution value, which is our maximum restitution every step, or the smallest gap between the 0 point and our current axis point. This will make sure it will always reach 0 exactly. Then we multiply it by the sine of our axis. So the sine is whether it's positive or negative, where if it's positive it will be 1, and if it's negative it will be minus 1. So in the end we're getting it in the correct direction for it to be subtracted. However, we still have a small problem. This will always take place right now as it is. However, we only want it to do so when we're not pressing any keys. And to do so is actually quite easy. Instead of using an if statement, which is actually quite slow, we can simply multiply it by axis underscore x underscore dir is equal to 0. Once again, we're actually taking advantage of the fact that Boolean values are represented as numbers. So axis x dir will only be equal to 0 if we are either pressing no keys or pressing both keys. So it will be that means that when axis x dir is equal to 0, this bracket over here will be equal to 1. So all of this will be multiplied by 1 and remain unchanged. So it will take effect if we're not pressing any keys. However, if we are pressing a key, axis x dir is equal to 0 will actually be equal to 0, because at this point, once we press a key, it is not equal to 0. So all of this will be multiplied by 0 over here, and therefore axis x sub will be equal to 0. It will therefore not make any effect. So we can copy and paste this code down below and just replace every x with a y, so that it does exactly the same thing but on the y-axis. And right now most of the work for axis calculation has actually been done. What we want to do now is actually add all this code to our axis. So we're going to do axis underscore x is equal to axis underscore x plus axis underscore x underscore add minus axis underscore x underscore sub. However, we have a small problem with this code. Right now, this could go, if we keep pressing right, the axis will get higher and higher and higher. So what we want to do is adding something called a clamp. So clamp, like so, and what clamp does, it will make sure that it will return a value which will either be the first argument or a minimum argument or maximum argument, making sure the value will always be between our min and max value. So right now we'll put in our min value, which is the minus axis underscore x underscore max, and our maximum value, which is of course axis underscore x underscore max. So this will just ensure that axis underscore x will always be between either minus axis x max or positive axis x max. Again, we can just copy and paste this for axis y. So we're just going to change all of this and replace the x's with y on this line. Here you go. Now, however, we have yet again another problem. That problem being that if we were to press both keys, up and right key, for example, we will be moving diagonally, and will not be moving at the speed we want. We'll actually be going far too fast. Let's open up OneNote and quickly illustrate what I mean. So right now, if we're moving along this axis like so, only towards the right, we'll be moving at, actually let me use a thicker pen because I'm not sure if this is going to be very clear on YouTube. If we're only moving to the right, we'll be moving at our maximum speed of 5. However, if on top of that we move upwards at a speed of 5, our total movement will actually be 5 squared, the square root of 5 squared plus 5 squared, which is actually greater than 5. If you want to know what it is, I could calculate it. 25 times 2. It's actually 7.1 about. So right now, instead of going, if we press both up and right at the same time, we're actually going at 7.1 pixels per second instead of the actual 5 that we want to go. So what we're going to do is normalize our axes. So normalize axis underscore x, axis underscore y. And what we're going to do is, well, first of all, we only want to do so if axis x and axis y are both not equal to 0. That is because, first of all, when we're going to do normalization, we're going to get a division by 0 error if we're going to have axis x and axis y equal to 0. And on top of that, if we don't really need to do it if we're not moving. If we're not moving, there is not much point in doing so. So we're going to go if not axis underscore x is equal to 0 and axis underscore y is equal to 0. So only if we are actually moving do you want to say that var dist is equal to the square root of the square axis x plus the square of axis y. So right now we're simply looking at the current speed we're going at, simply by taking this, by doing a Pythagorean triangle with our axis x and axis y and finding the hypotenuse. What we want to do now is find the actual distance that we're allowed to move at. So var mdist is equal to the minimum between movement speed, movement speed, and our dist. So what we're doing here is making sure that mdist will be equal to dist, but always smaller than movement speed. So this means that we're basically making dist smaller than movement speed, or smaller or equal to movement speed. Now we're going to be normalizing our axis. So axis x is equal to axis x divided by distance. So right now we're normalizing it, making sure our vector of axis x, axis y has a length of 1, and timesing it by the actual speed we're allowed to go at, mdist. Same with axis y. So axis y is equal to axis underscore y divided by dist times mdist. So for those of you who are not familiar with vectors, what we're doing right now is treating x and axis x, axis y as a vector, and basically to find the length of a vector, you take the square roots of the sum of the square of both values. So this will give us the length. Now if you divide each component of the vector, so axis x and axis y, by its length, you make sure that the vector itself only has a length of 1. And now we're timesing it by mdist, which is the length we wanted to have it. So if we multiply both components by mdist, we make sure the overall vector has a length of mdist. So right now our vector will always have a length of smaller or equal to 5, which means that no longer can we go faster by pressing up and right at the same time. So now all that's left to do is actually add the movement code. So we're going to add the very simple movement code for now. Simply x plus is equal to axis underscore x and y plus is equal to axis underscore y. So this is the very simple code. We're going to have to change this later in order to add collisions, but I thought that we've been doing a lot of code and not much testing. So here it is. Our object is now in the room. Press OK. Let's just save it quickly and press play. So what we should be able to do now is simply move up, down, left, right using both the keyboard keys and the WASD. So as you can see, I can move up and down like so. And as you can see, it is very, very smooth. If I press up, you can see the acceleration. When I release the key, there is a very subtle deceleration, which really makes it quite comfortable to use. You know, it's not choppy at all. And right now I can also use the W, A, S, and D keys. If I press all the keys at the same time, you can see I'm not moving because our axes are taking care of that, which actually stops the sticking keys problem when you try to when you play some games. And overall, it feels really quite nice. So already we have a nice system. However, you can see that I can pass through walls. So what we have to do now is add a collision system. So a simple collision system is actually quite easy to implement. So if we go back into our movement code, we can add already quite a simple collision system, as I said. Simply going, well, first of all, we're not going to do the collision checking if we're not moving. So if not axis underscore x is equal to 0 and axis underscore y is equal to 0, and we're going to add our collision checks. Now you may have noticed we already have an if statement over here, so actually what we're going to do is get rid of this if statement over here and simply make use of the if statement we already created before. And we're going to go move. So what we're going to use, in order to check for collisions is a function called placeMeeting. What it does is it tells you whether your object at a given position will collide with an object or not. It is really, really quite useful. So if place underscore meeting x plus axis underscore x, y plus axis underscore y, obj underscore par wall. And then we put our curly brackets in and make sure that x plus is equal to axis x and y plus is equal to axis y only works if we do not have a place meeting. So remember to put your exclamation mark in front of place meeting. So what we're saying here is actually quite clever. We're telling the computer to check whether there will be a collision if we move our object at a position x plus axis x and y plus axis y. What it means is that if there will be a collision, well, we're not going to be moving. And if there isn't a collision, then we do a movement. This means we won't be colliding with objects. However, there is a drawback. If I press play right now and try to move towards an object, as you can see, I get stuck sometimes just before that object. As you can see, the collision works, obviously. However, as you can see right here, for example, I get stuck within the object, and this is no good. And it is a problem because we want it to be not so choppy when you hit the walls. We actually want it to go all the way and hit the wall, not stop right in front. So what we're going to do in order to remedy this problem is add a bit of code. So first of all, we're going to take off. No, never mind. We're not going to take this off. We're going to add an else statement. So if there is indeed a collision, what we want to do is move towards that wall progressively. And we're going to do so separately for the x and the y-axis, so that if you do get stuck on the y-axis, for example, against a wall that's on top of you, you can still move left and right. So this isn't too hard to do. In fact, it's quite simple to do. What we're going to do is use a for statement, a for loop. We're going to say var I, because is equal to 0. Then we want to make sure I is smaller than the absolute value of our axis. Now the reason why we're using the absolute value of it is that we don't want we want it to work both ways. We want it to work if you're moving in the positive direction. We also want it to work if you're going on a negative direction. And next we want to simply add 1 to our I. So we're going to increment using I++. Add in our curly brackets, and now what we want to do is check whether there's a collision. So if place meeting, we're just going to copy this over here actually. If place meeting over here, take off the y part because we're only doing for the x-axis at the moment. So if place meeting x plus x-axis y is and with object power wall, we want to break the loop. So basically, as soon as we get the collision, stop moving. Oh yeah, by the way, it shouldn't be x plus x-axis over here. It should be x plus sine of x-axis. Axis underscore x. The reason for this is quite simple. If x-axis, well, right now what we're doing is moving them pixel by pixel until we hit the wall. So what we want to do is, just like before, check if if we're moving to the right, we want to check one pixel to the right, see whether there's a collision, and if we're moving towards the left, we want to check one pixel towards the left. And so a nice and easy way to do this is simply to check what direction we're moving in using sine, which will return the sine of our number, and add it to x. So we're breaking the loop if there is a collision. If not, so simply underneath, x plus is equal to sine of axis underscore x. Now, again, we're using sine because we're moving him pixel by pixel. We don't want him to move all the way from axis x. So sine basically makes sure that axis x is between, is snapped to -1, 0, or 1. What we can do now is do the exact same thing for the y. So I'm going to copy this whole for loop and paste it over here. We can simply change our axis y values to axis y, and make sure that instead of having if place meeting x plus x-axis, we want to have x, y plus sine axis underscore y, because we want to do it for the y-axis now. And we're gonna do over here for the movements, y plus is equal to sine of axis y. So that is it for the collision. If I press save now and press play, what you will see is that our player can now move and collides a lot nicer with our walls. It will go all the way to the wall and collide with it. Now actually, our triangles don't work at the moment because I forgot to do something quite important actually, and what it is actually really simple to fix. Simply go to SPR wall corner, modify the mask. As you can see right now, the whole mask is covering the entire sprite. However, we want it to be a triangle because that is what our object is. Now, unfortunately, there isn't a triangle mask. They should really add that in. Instead, we're going to use a precise collision. Now, this is quite a bad habit because precise collision is slow. However, there is no alternative. So we're just going to have to make do. Press OK once you check precise. OK. Another change we want to do is inside our player object, modify the mask and make sure you choose ellipse. This is because our player right now is a circle, and so we want it to also use an ellipse. Now what's nice about ellipse is that it's actually the same as precise pretty much. You can see it's actually slightly more circular because masks tend to be use another system for calculating the circles. However, it is much faster than using the precise collision. So we're going to just select ellipse, press OK, now save again, and if we press play, you should see that the triangles will now collide perfectly. If I go towards a triangle wall, as you can see, I go all the way nice and snugly towards a triangle, and I get absolutely, it's just a very nice collision system, because as you can see, I can also slide across this even though I'm still pressing down. A lot of different collision systems will result in your plane getting stuck when you do so, and you have to let go of the down key in order to go left and right. But here I can still press left, I can still press down and go left and right. All that it has to do now is calculate the direction in which we're facing. Now the way we're going to do this only really works with our sprite facing downwards. So this is why I said we should face it downwards. And we're just going to put this code right over here at the end of our if statement that checks whether we're moving or not. So, just before the last bracket. And what we're going to write is, sorry, this is supposed to be indented like so, is that our facing angle is equal to darctan 2, axis x, axis y. Now, darctan 2 is a very, very interesting and powerful trigonometric function. First of all, what is it? It's basically the arctan function, so the inverse function of tan. So if I bring up OneNote, I can explain why we're using this. So let me create a new... I can't really do that. Let me just erase all of this and quickly explain why we have to use such a function and why it is so powerful. So right now what we have is a vector which has, you know, it may be like so, and has some x component and some y component. We can, of course, we can rewrite this vector, we can redraw this by taking our line over here and placing it right over here. So this is our x and y. As you can see, it creates a Pythagorean triangle. What we want to do is find this angle over here, theta. Now tan of theta is equal to the opposite over the adjacent. So it's equal to y over x. So in order to get theta, we need to use the inverse function, arctan, of y over x. However, there's a problem. If x is equal to 0, we get a division by 0 error. And that's generally quite bad. Now there's quite a few ways to go around it. One of them is simply to use an if statement to check whether x is equal to 0 or not, or make sure x is always equal to a tiny bit higher than 0, etc. However, none of these are desirable. This is why GameMaker gives us a function called arctan 2, which will allow you to, instead of saying y over x, we can give y and then x. So we do axis x, axis y. Now, we do them the other way around because of the direction in which our angles are going. And the reason why we're using darctan 2 is that we want to have facing angle in degrees, not in radians. Now, in order to see the effect that facing angle has, we need to go into Add Event, Draw, and we're going to add some code in, draw underscore sprite underscore x, our sprite index, our subimage, so image insert index, our x and y position, our x scale and y scale, which is 1 and 1, we're not going to change this ever. Now our rotation, which is facing underscore angle, the color is C white, and the alpha is 1. Press OK, save it, and now what we should see is that our player is facing in the correct direction. If I move right, as you can see it's moving right. If I press up, you can see that really the fluidity of the movement is just really nice, even though it is only, well, essentially it is originally, you know, 8-directional. However, because we're using these axes, you get a very nice movement. Our collision still works nicely. And yeah, now this movement can be used for all sorts of different, you know, games. You can use it for any kind of top-down shooter games. It could be a tank, it could be just a person, of course. You could use it for, I don't know, it could be a side-scrolling game where you can move left and right. Now, of course, the direction would obviously work a bit differently, but you know, what's nice about it is that you can have different acceleration values, and the nice movement will give it much more fluidity if you're making a side-scrolling, you know, plane shooter game or some sort. So yeah, so this is it for our smooth movement and collisions. I hope you found this video useful, whether it was the smooth movement aspect of it or maybe just the collisions. And I'll see you guys next time for more videos. If you have any questions, please post them down below. If you have any suggestions for any future videos, please do so. So if you enjoyed, please like and subscribe, it truly helps. And I'll see you guys next time.